Most people assume that humanity's greatest journey into deep space is already underway. Somewhere beyond the outer planets, Voyager 1 continues its silent voyage toward the stars, carrying the farthest reach of human civilization into an ocean of darkness. It is easy to believe that this story has already been written. The spacecraft is flying outward, the mission is nearly complete, and eventually another probe will simply follow the same path. Yet the universe rarely allows history to repeat itself so neatly. The route that carried the Voyagers across the giant planets was never an ordinary path through space. It was a fleeting arrangement of worlds that existed only for a brief moment in the history of our solar system. By the time those two spacecraft left Earth in 1977, a cosmic opportunity that appears only once every century and 3/4 had already begun to disappear behind them. This presents an unexpected paradox. Technology has advanced beyond anything the engineers of the 1970s could have imagined. Our computers are millions of times faster. Our spacecraft survive environments once thought impossible. We have landed on comets, flown through the atmosphere of Saturn's moon Titan, and touched the outer edge of the Sun itself. Yet despite all of that progress, sending another spacecraft beyond the solar system has become in some ways more difficult than it was nearly 50 years ago. The challenge is not simply building a better machine, it is finding a new road through a changing solar system. Because the road that Voyager followed no longer exists. This quiet realization has transformed the way scientists think about the future of exploration. Instead of asking how to build another Voyager, they have begun asking a far more ambitious question. If nature no longer offers us the perfect gravitational pathway across the planets, can we create one ourselves? The answer surprisingly may lie much closer to home than Jupiter or Saturn. It may lie beside the very star that holds our entire planetary family together. For generations, the Sun has represented a barrier. Every spacecraft leaving Earth first struggles against its enormous gravity. Every planet circles within its influence. Every comet returning from the darkness eventually falls back towards its warmth. The Sun appears to imprison everything within its reach. But modern orbital mechanics reveals something unexpectedly elegant. Under precisely the right conditions, the same gravity that binds every planet may also become the greatest accelerator humanity has ever possessed. Not by escaping the Sun, but by falling toward it first. At first glance, the idea seems almost contradictory. Why would a mission designed to leave the solar system begin by diving deeper into it? Why would engineers intentionally send an expensive spacecraft toward the hottest environment any human machine has ever encountered? The answer belongs to a subtle principle hidden within gravity itself. Motion and energy are not distributed equally throughout an orbit. There are moments when a tiny change produces only a tiny result. There are other moments when the exact same effort produces consequences many times greater. Nature quietly rewards perfect timing. For nearly a century, physicists have understood this remarkable feature of orbital motion. Only recently have engineering materials, science and spacecraft design begun approaching the point where it could become practical. That possibility has inspired one of the most ambitious concepts ever seriously studied for deep space exploration. It does not officially carry the name Voyager 3. There is no polished spacecraft sitting inside a clean room with those words painted across its side. There has been no dramatic launch announcement, no countdown clocks, no famous photographs of engineers celebrating beside a completed vehicle. Instead, the mission exists in drawings, simulations, thermal models, trajectory, calculations, laboratory experiments, and thousands of hours of careful scientific work. Quietly over many years, researchers have assembled a blueprint for something that could travel farther than any spacecraft before it, while reaching extraordinary distances in a fraction of the time. Its official name is the Interstellar probe. Names, however, often conceal deeper stories. Just as Voyager represented much more than two robotic spacecraft, the Interstellar probe represents far more than another scientific mission. It represents a change in philosophy. Instead of visiting worlds one after another, its destination is the vast region between stars themselves. That distinction matters. For centuries, astronomy has mostly been an act of observation. Telescopes remained close to Earth while their mirrors gathered distant light. Even space telescopes floating far above our atmosphere continue observing the universe from essentially the same small neighborhood. The Voyagers changed that relationship forever. For the first time, humanity carried scientific instruments into regions where no telescope could ever reach. Now, a new generation of scientists hopes to extend that journey hundreds of billions of kilometers farther. Not merely to leave the solar system, but to look back upon it. To see our entire cosmic home from outside the invisible bubble carved by the solar wind. To measure directly the environment that exists between the stars. To understand where the influence of our sun truly ends and where the wider galaxy begins. These goals may sound distant, almost poetic, yet they arise from remarkably practical scientific questions. The boundary surrounding our solar system affects cosmic radiation magnetic fields, charged particles, and the very environment through which every future interstellar mission must someday travel. Before humanity can dream seriously about journeys to neighbouring stars, it must first understand the ocean that lies between them. That realization transforms the mission into something larger than a successor to Voyager. It becomes humanity's first deliberate attempt to explore interstellar space as a destination, rather than merely a milestone. And once that idea takes hold, another question quietly emerges. If reaching interstellar space is no longer the final objective, but only the beginning of an even greater voyage, how should such a spacecraft actually leave the solar system in the first place? The answer begins not among the distant planets, but with the remarkable history of two aging spacecraft that have already shown us what is possible. The two Voyager spacecraft began their journey at a moment that in retrospect appears almost impossibly fortunate. When Voyager 1 lifted away from Earth in September of 1977, followed only weeks later by Voyager 2, they were not simply beginning long voyages toward the outer planets. They were taking advantage of a celestial arrangement that had been quietly unfolding for millions of years. Giant worlds that normally wandered through the solar system with little regard for one another had aligned in just the right sequence to create a natural highway across billions of kilometers of space. Nothing about that highway was built. Nothing about it was permanent. It existed because the slow clockwork of planetary motion had briefly arranged Jupiter, Saturn, Uranus, and Neptune into a pattern that gravity itself could exploit. To appreciate how extraordinary this opportunity was, it helps to think of the solar system not as a collection of stationary planets, but as a vast choreography. Every world circles the sun at its own pace. Mercury completes an orbit in just 88 days, Earth requires 1 year, Jupiter takes almost 12 years while Neptune needs 165. Each planet is constantly moving. Their positions are never fixed. Most of the time, a spacecraft leaving Earth can certainly reach another planet, but visiting several giant planets in succession becomes extraordinarily expensive. Every change in direction demands additional fuel. Every increase in speed carries a heavy cost. The farther a spacecraft travels, the more difficult each new destination becomes. Gravity offers an elegant solution. Whenever a spacecraft flies close to a massive planet, it does not simply pass by. It briefly enters a delicate gravitational dance. If engineers calculate the trajectory with remarkable precision, the spacecraft can borrow a tiny fraction of the planet's orbital momentum. The planet loses an immeasurably small amount of energy, while the spacecraft leaves travelling significantly faster than before. This is known as a gravity assist. The principle is surprisingly gentle. Nothing collides, nothing explodes. Instead, gravity quietly exchanges energy according to the same physical laws that govern every orbit in the solar system. The concept had existed in mathematics long before it became reality. Yet it was during the 1960s that a young engineer named Gary Flandreau noticed something remarkable while studying possible planetary missions. He realized that during the late 1970s, the outer planets would align in such a way that a single spacecraft could visit several of them using successive gravity assists. The opportunity would not return for roughly 175 years. Suddenly, an idea that had seemed almost impossible became achievable. One spacecraft could leave Earth, accelerate around Jupiter, gain additional speed towards Saturn, and if everything proceeded perfectly, continue onward toward Uranus and Neptune. It was less like driving from one destination to another, and more like crossing a river by stepping across stones that happened to appear above the water. Miss one stone and the entire crossing became impossible. NASA recognized the significance immediately. Originally, the vision was even larger than what history remembers. Early plans proposed 4 spacecraft participating in what engineers called the Grand Tour. Together, they would explore all of the giant planets using this unique alignment, providing humanity with its first close examination of the distant solar system. Reality, however, rarely matches ambition without compromise. Budget limitations gradually reduced the scope of the mission. Political priorities shifted. The enormous financial demands of the Apollo era still shaped national decisions. Eventually, the 4 spacecraft became 2. Those 2 survivors would carry the hopes of the entire project. Even then, success remained uncertain. No spacecraft had ever attempted anything comparable. Every planetary encounter depended upon the previous one unfolding almost perfectly. Small navigational errors could grow into enormous deviations over billions of kilometers. The computers aboard the spacecraft possessed less memory than many ordinary household devices today, yet they were expected to navigate one of the most complicated journeys ever attempted. Against remarkable odds, they succeeded. Voyager 1 transformed our understanding of Jupiter's volcanic moon, Io, revealing active volcanoes erupting hundreds of kilometers above its surface. Until then, Earth had been the only known world with active volcanism. Soon afterwards, Saturn unveiled equally unexpected wonders. Its rings, once appearing smooth through telescopes, resolved into countless delicate structures. Thin ringlets braided together, gravitational interactions with tiny moons sculpted intricate patterns across vast disks of ice. Titan emerged beneath its dense orange atmosphere as an entirely different kind of world, hiding lakes and rivers that later missions would eventually explore. Voyager 2 continued even farther. It became the first and still the only spacecraft ever to visit Uranus and Neptune. At Uranus, astronomers encountered a planet rotating almost on its side, surrounded by dark rings and strangely tilted magnetic fields. Neptune revealed powerful storms racing through an atmosphere of hydrogen, helium, and methane, despite receiving only a fraction of the sunlight that warms Earth. Each encounter answered old questions while creating new mysteries. Every planet appeared more complicated than expected. Every moon became its own world. The solar system, once imagined as a collection of simple spheres circling the sun, revealed itself as a richly diverse family of environments, shaped by billions of years of geological and atmospheric evolution. Yet perhaps the Voyager's greatest achievement was not any single planetary discovery. It was their endurance. Long after completing their original mission objectives, both spacecraft continued outward into regions no human instrument had ever explored. Their cameras were eventually switched off to conserve precious electrical power. Planetary photography gave way to something quieter but equally profound. The spacecraft became laboratories for studying the invisible. They measured charged particles streaming outward from the sun. They monitored magnetic fields threading through space. They listened to faint plasma oscillations traveling through regions where sunlight had become little more than another bright star. Gradually, year after year, the familiar influence of the sun weakened. The solar wind slowed. Cosmic rays increased. The environment surrounding the spacecraft changed so subtly that only decades of patient observation revealed what was happening. Without fanfare, the Voyagers approached the edge of humanity's cosmic neighborhood. They were no longer explorers of planets. They had become explorers of the space between stars. It is tempting to assume that another spacecraft could simply repeat this remarkable journey with better instruments and faster computers. But the success of Voyager depended upon something far older than technology. It depended upon the precise arrangement of worlds that no longer exists. If those celestial stepping stones have now drifted apart, then the path that carried humanity to the threshold of interstellar space has quietly vanished. The question that follows is unavoidable. If gravity once opened a temporary highway across the solar system, what road remains for the explorers who wish to follow? For a long time, it seemed reasonable to believe that the Voyager missions had established a blueprint for the future. Build a spacecraft, launch it toward Jupiter, borrow the giant planet's gravity, continue outward, repeat. From a distance, the process appears almost timeless, as though the solar system patiently waits for each new generation of explorers to begin the same journey. But the solar system is not a fixed landscape. It is a moving one. Every planet, every moon, every asteroid traces its own orbit around the Sun with unwavering precision. Day by day, the changes are almost invisible. Century by century, they become profound. A pathway that once existed gradually dissolves, not because anything dramatic has happened, but because celestial mechanics never stand still. The Voyagers succeeded because they departed during an exceptionally rare alignment of the outer planets. Jupiter stood in precisely the right position to accelerate the spacecraft towards Saturn. Saturn, in turn, occupied the right location to redirect Voyager 2 toward Uranus. Uranus later provided the final gravitational step toward Neptune. Each encounter depended upon the previous one. Remove a single link from that chain and the entire sequence collapses. This is what makes the Voyager missions historically unique. Their success was not merely the product of brilliant engineering. It was also a gift from orbital geometry. The planets themselves became part of the spacecraft's propulsion system. That realization changes the way we think about exploration. When we speak of the Voyagers, we often celebrate the remarkable spacecraft. Less often do we remember that Jupiter, Saturn, Uranus, and Neptune were equally important participants in the mission. Without their precisely timed motions, the journey would have required far more fuel than any launch vehicle of the 1970s could possibly provide. Gravity performed the heavy lifting. The spacecraft simply knew how to ask. This delicate partnership between engineering and celestial mechanics cannot be recreated on demand. Jupiter still circles the Sun every 12 years. Saturn continues its patient 29-year orbit. Neptune remains nearly 165 years from completing a single revolution. Yet they're no longer arranged like stepping stones stretching toward interstellar space. Instead, they have drifted into entirely different positions. A spacecraft launched today could certainly visit Jupiter. It could also reach Saturn. With enough fuel and enough time, future missions will undoubtedly return to Uranus and Neptune as well. But visiting all 4 giant planets with a single sequence of nearly effortless gravity assists has become impossible for the foreseeable future. The cosmic train has already departed. This is one of those subtle facts that rarely attracts attention outside the scientific community. Technology advances every year. Rocket engines become more efficient. Computers become more powerful. Materials become stronger. Naturally, we assume that every challenge should therefore become easier. Orbital mechanics reminds us that nature does not always reward technological progress in such a straightforward way. Some opportunities are governed not by engineering but by time itself. The alignment that launched the Voyager era emerged from millions of years of planetary motion. Human civilization happened to appear during one brief interval when that opportunity existed. The next comparable alignment will not occur until well into the 22nd century. For the scientists working today, waiting is not a practical strategy. No engineer designing a spacecraft today expects colleagues born more than a century from now to oversee its launch. Exploration must proceed with the solar system. We have not the one we wish we had. That realization forced mission designers to ask an entirely different question. If the outer planets can no longer provide the necessary energy, where else might it come from? At first glance, the answer seems obvious. Carry more fuel. Modern rockets are vastly more capable than those that launched the Voyagers. Heavy lift vehicles can place larger payloads into space. Advanced propulsion systems continue to improve. Surely greater power alone could compensate for the missing planetary alignment. Unfortunately, physics remains stubbornly indifferent to optimism. Every kilogram of additional propellant requires additional structure. Additional structure increases mass. Greater mass demands even more propellant. Engineers know this relationship well. It is described by the rocket equation, one of the most unforgiving principles in aerospace engineering. The equation contains no loopholes. Adding more fuel eventually produces diminishing returns. Beyond a certain point, the spacecraft spends most of its fuel carrying more fuel. This is why gravity assists became so valuable in the first place. They provide energy without requiring the spacecraft to carry it. Nature contributes the acceleration. The spacecraft simply follows the correct trajectory. Without the rare planetary alignment, engineers faced an uncomfortable truth. The old solution was gone. An entirely new source of energy had to be found. Some researchers explored advanced electric propulsion, where gentle but continuous thrust gradually builds enormous speed over many years. Others examined nuclear propulsion concepts capable of producing much greater efficiency than chemical rockets. Still others investigated solar sails, allowing sunlight itself to push spacecraft outward through space. Each approach offered intriguing possibilities. Each also introduced difficult compromises involving mass complexity, cost or mission duration. None fully replaced what the outer planets had once provided almost effortlessly. The search continued. Ironically, the answer had been hiding in plain sight from the very beginning. Every spacecraft leaving Earth struggles against one overwhelming force. Not Jupiter, not Saturn, the Sun. Nearly all of the energy required to escape the solar system is spent overcoming the gravity of the star at its center. The farther a spacecraft travels from the Sun, the weaker that gravitational grip becomes. But close to the Sun, gravity is immense. Objects there move with astonishing speed as they fall through the deepest part of the Sun's gravitational well. For centuries, that immense gravity had been viewed only as an obstacle. Yet orbital mechanics suggests another perspective. Perhaps the deepest gravity well in the solar system is not merely something to escape. Perhaps it is something to use. That possibility sounds almost contradictory. Why would a mission intended to leave the solar system first travel inward toward temperatures capable of melting metal and radiation, intense enough to challenge the limits of modern engineering? The idea seems to violate intuition, and yet the mathematics quietly insists otherwise. Hidden within the equations of orbital motion is a remarkable principle first recognized nearly a century ago. It suggests that the fastest route away from the Sun may begin by falling dangerously close to it. If that principle can be transformed from elegant mathematics into practical engineering, humanity may no longer need the rare generosity of planetary alignments. Instead, every future journey to interstellar space could begin with the same unlikely destination, our own star. Every great journey begins with a question that seems impossible at first. For the engineers who inherited Voyager's legacy, the question was not whether another spacecraft could reach interstellar space. Eventually, given enough time, almost any spacecraft moving away from the Sun will do exactly that. The real question was different. Could a spacecraft reach interstellar space within a single human lifetime while carrying instruments vastly more capable than those launched nearly half a century ago? That challenge demanded something more than incremental improvement. It required rethinking the journey from its very beginning. The Voyager missions had demonstrated the extraordinary power of gravity assists, but those assists depended upon the positions of distant planets. Since the celestial arrangement of the late 20th century could not be recreated, engineers began searching for entirely different trajectories. Instead of asking which planets should accelerate the spacecraft, they asked a more fundamental question. What is the greatest source of energy already present within the solar system? The answer had always been obvious. It simply had not been viewed from the right perspective. Everything in the solar system owes its motion to the Sun. Every planet, every comet, every asteroid, and every spacecraft moves within its enormous gravitational field. The Sun contains more than 99% of all the mass in the solar system. Jupiter may dominate the planets, but compared with the Sun, it is almost insignificant. If gravity could provide acceleration, then surely the greatest gravitational field available offered the greatest opportunity. The difficulty lay in reaching it. Most spacecraft are designed to travel outward. Their trajectories gradually climb away from the Sun, trading speed for distance. Every kilometre travelled outwards slightly reduces their velocity as solar gravity slowly pulls against them. A mission that intentionally dives toward the Sun follows the opposite path. Instead of climbing, it falls. As it descends, gravity steadily increases its speed. The spacecraft races faster and faster, converting gravitational potential into kinetic energy. Near the Sun, orbital velocities become astonishing. Mercury, the innermost planet, circles the Sun at nearly 48 kilometers every second. A spacecraft passing even closer can move dramatically faster still. This enormous velocity caught the attention of mission planners, not because they wished to remain near the Sun, but because of what becomes possible at the moment of greatest speed. For decades, orbital mechanics had contained a beautiful principle known to specialists, but rarely discussed outside aerospace engineering. A rocket engine does not always produce the same result. Burning a kilogram of fuel in one part of an orbit may generate a modest increase in energy. Burning that identical kilogram while travelling much faster can produce a dramatically larger increase in the spacecraft's final trajectory. The engine itself has not changed. The fuel has not changed. Only the timing. Nature quietly rewards acceleration applied at maximum velocity. This principle, first described by the German pioneer Hermann Oberth during the early 20th century, remained largely theoretical for many years because few missions could fully exploit it. Now, however, engineers began to realize that it might solve exactly the problem facing a modern Voyager successor. Instead of relying on a rare alignment of planets, perhaps the spacecraft could create its own extraordinary departure speed by combining three separate elements: a powerful launch from Earth, a carefully planned gravity assist from Jupiter, and finally an extraordinarily close dive toward the Sun before igniting its propulsion system at precisely the moment when physics offered the greatest reward. It was an idea at once elegant and intimidating. Elegant because it relied upon well-understood physics. Intimidating because it demanded flying closer to the Sun than almost any spacecraft had ever attempted. For generations, such a trajectory would have been dismissed almost immediately. The thermal environment alone appeared overwhelming. Closer to the Sun, sunlight grows dramatically more intense. Heat increases not gradually, but according to the inverse square law. Halving the distance to the Sun does not merely double the solar energy, it quadruples it. Approach within only a few solar radii and the spacecraft enters an environment unlike anything encountered elsewhere in the solar system. Temperatures become extreme. Radiation intensifies. Every exposed surface experiences conditions capable of destroying conventional spacecraft materials. Only recently has humanity begun proving that survival in such an environment may actually be possible. One mission launched decades after Voyager quietly changed expectations. The Parker Solar Probe was built for an objective once considered almost unreachable. Rather than escaping the Sun, it repeatedly plunged toward it, each orbit carrying it deeper into the solar corona than any spacecraft before. Protected by an advanced carbon composite heat shield, Parker demonstrated that modern engineering could endure conditions previously thought unattainable. Its success transformed an abstract possibility into something much more tangible. Scientists now possessed real data, real temperatures, real material performance, real operational experience. The Sun had not become less hostile. Human engineering had simply become more capable. That change in confidence encouraged researchers working on an entirely different mission. If Parker could repeatedly survive extraordinary proximity to the Sun, perhaps another spacecraft could venture similarly close while carrying out a very different objective. Not to study the Sun itself, but to use it within laboratories and research centers. Trajectory specialists began running countless simulations. Every calculation explored tiny adjustments, a slightly different Jupiter flyby, a slightly different approach angle, a slightly different engine burn. Thousands of possible paths were examined, each seeking the same outcome: maximum speed, minimum risk, acceptable engineering complexity. Unlike the dramatic launches often celebrated in documentaries, this phase of exploration unfolded quietly. No rockets fired, no spacecraft flew. Instead, discoveries emerged from equations, computer models, and years of patient refinement. Little by little, an extraordinary mission profile began taking shape. It would not exactly repeat Voyager, neither would it replace Voyager. Instead, it represented a completely new philosophy of exploration, The giant planets would no longer serve as a staircase leading outward through the solar system. Instead, Jupiter would become only the first step. The real acceleration would come much later during an encounter with the very object that every previous deep space mission had spent its entire journey trying to leave behind, the Sun itself. And if the calculations were correct that single encounter could propel humanity's next great explorer toward interstellar space at speeds once thought unattainable, the question was no longer whether such physics was possible. The question had become whether engineers could transform elegant mathematics into a spacecraft capable of surviving the most demanding journey ever attempted. By the time a mission concept receives an official name, years of quiet work have usually already passed. Long before rockets are assembled or instruments are installed, scientists fill notebooks with calculations. Engineers build computer models that no member of the public will ever see. Every assumption is questioned. Every weakness is tested. Entire careers can unfold before a single piece of hardware is constructed. The mission that many people casually call Voyager 3 has followed precisely this path. Its official name is the Interstellar Probe. The title is remarkably simple, almost understated considering the scale of its ambition. Rather than emphasizing speed or technology, it describes only its destination. Interstellar space. That choice of words reflects a subtle shift in scientific thinking. When the Voyager spacecraft launched in 1977, interstellar space was almost an abstract concept. Astronomers understood that the solar system existed within a much larger galactic environment, but the invisible boundary between them remained largely theoretical. The heliosphere, the enormous bubble carved by the solar wind, had never been crossed. Nobody knew exactly where it ended. Nobody knew how its boundary behaved. Nobody had measured the transition directly. Voyager transformed those questions into observations. Decades later, the Interstellar Probe proposes something different. Instead of merely reaching that boundary as the final chapter of its mission, it intends to begin its most important scientific work only after crossing it. That distinction changes everything. The spacecraft is no longer designed as a planetary explorer. It is being designed as an observatory for the space between stars. The concept has been developed over many years by researchers led through the Applied Physics Laboratory of Johns Hopkins University, working alongside scientists from NASA and institutions across the world. Hundreds of specialists have contributed to the evolving design. Their expertise ranges from heliophysics and plasma science to spacecraft engineering, thermal protection, communications and trajectory analysis. Unlike many ambitious ideas that exist only as rough sketches, the Interstellar Probe has matured through repeated technical studies. Its proposed trajectories have been calculated in extraordinary detail. Its scientific objectives have been carefully prioritized. Its engineering challenges have been examined from multiple directions. This is not a dream waiting for physics to catch up. It is a mission waiting for approval. If selected, current planning envisions a launch sometime during the late 2030s or early 2040s. That schedule may seem distant. Space exploration often unfolds on timescales unfamiliar to everyday life. Large observatories, planetary probes, and flagship missions frequently spend decades moving from proposal to launch. Instruments must survive environments that cannot be repaired. Every component is expected to operate reliably after years of travel through deep space. Patience becomes part of the engineering. Once launched, the Interstellar Probe would first escape Earth's gravity aboard a powerful launch vehicle. Its earliest months would resemble many previous deep space missions. Earth would gradually shrink behind it. The Moon's orbit would disappear into the distance. The planets would slowly rearrange themselves across the dark background of space. Yet unlike Voyager, whose greatest planetary encounters became international spectacles, this mission would spend much of its early life preparing for a single crucial event, its encounter with Jupiter. At first glance, this seems familiar. After all, Jupiter has accelerated numerous spacecraft before. Pioneer, Voyager, Ulysses, Cassini, New Horizons. Each borrowed energy from the giant planet while continuing toward a different destination. The Interstellar Probe intends to do the same. But this gravity assist serves an entirely different purpose. Voyager used Jupiter as the first link in a chain leading towards Saturn. The Interstellar probe uses Jupiter as preparation for something much more demanding. The spacecraft must redirect itself toward an orbit that falls inward toward the Sun. This reversal feels almost counterintuitive. After spending years climbing away from the Sun, the spacecraft deliberately turns back. It willingly descends into the deepest part of the solar system's gravitational well. From a distance, the trajectory resembles an archer pulling a bowstring backward before releasing the arrow. The backward motion is not failure, it is preparation. Every kilometer fallen toward the Sun increases the spacecraft's speed. Every hour spent descending stores more energy for what comes next. The timing of this inward journey becomes extraordinarily precise. A slight deviation of only fractions of a degree could dramatically alter the spacecraft's closest approach. Engineers must account for countless influences: planetary gravity, solar radiation pressure, tiny navigation corrections, the gradual performance of onboard propulsion systems. Nothing can be left to chance, because everything depends upon arriving at exactly the right place, traveling at exactly the right speed. Only then can the next phase begin. One of the remarkable aspects of the mission is how modest the spacecraft itself may appear. People often imagine revolutionary exploration requiring gigantic vehicles. History tells a different story. Voyager weighed less than a small automobile. New Horizons, which explored Pluto, was smaller still. The value of an interstellar mission lies not in physical size, but in the precision of its trajectory and the sophistication of its instruments. The Interstellar probe follows that same philosophy. Every kilogram must justify its existence. Additional mass requires additional energy. Additional energy increases engineering complexity. Mission designers therefore treat weight almost as a precious resource. Scientific instruments compete with communication systems. Power generation competes with structural reinforcement. Every decision reflects careful compromise. Even the mission duration demands unusual thinking. Unlike most scientific projects, the Interstellar probe is expected to remain operational for at least half a century. Some estimates extend considerably longer. This means engineers designing the spacecraft today must anticipate technology's scientific priorities and operational challenges that may not fully emerge until many decades after launch. Few other fields ask people to build machines intended to outlive their own professional careers. Yet deep space exploration has always required this remarkable form of optimism. Each generation constructs bridges that the next generation will eventually cross. The Interstellar probe represents one of the longest bridges humanity has ever attempted to build. Its destination lies not merely beyond the planets, but beyond the invisible frontier where the influence of our Sun gradually gives way to the wider galaxy. Reaching that frontier is an extraordinary challenge. Crossing it is only the beginning, because the true power of the mission may ultimately depend upon the remarkable maneuver that still lies ahead when the spacecraft approaches closer to the Sun than almost anyone would instinctively believe possible. For most of human history, the Sun has represented the beginning and the end of every journey. It lights our skies. It governs the rhythm of the seasons. Its gravity keeps every planet faithfully circling through space. Even the most distant objects in the solar system remain tied to it, however loosely, by an invisible thread of gravity stretching across trillions of kilometers. It seems almost contradictory that the fastest route away from the Sun could begin by moving closer to it. Yet nature is often at its most elegant when it appears least intuitive. To understand why we must momentarily set aside the familiar image of a rocket forcing its way through space. Spacecraft do not travel the way ships cross an ocean. A ship moves through water, pushing against it with every turn of its propellers. Space offers nothing to push against. Instead, every spacecraft follows a path shaped almost entirely by gravity. Once its engines stop firing, it simply falls. Not downward in the everyday sense, but continuously around whatever object dominates its surroundings. Earth falls around the Sun, the Moon falls around Earth. The International Space Station falls around Earth every 90 minutes. Even the Voyagers, now hundreds of astronomical units away, are still slowly falling within the immense gravitational influence of the Sun. The remarkable thing is that falling can become extraordinarily fast. Consider a stone dropped from a rooftop. It accelerates because gravity converts height into motion. The farther it falls, the faster it moves. Now replace the rooftop with the solar system itself. A spacecraft beginning far from the Sun possesses a certain amount of orbital energy. As it descends toward our star, gravity steadily transforms that stored energy into velocity. By the time it approaches the Sun, the spacecraft is moving faster than it ever could near Earth. This is not because its engines have become stronger. It is because gravity has done the work. At this stage, something extraordinary becomes possible. Suppose two identical spacecraft each carry the same amount of fuel. The first fires its engine while drifting far from the Sun. The second waits until it has fallen deep into the Sun's gravitational well before igniting exactly the same engine for exactly the same amount of time. Common intuition suggests both spacecraft should receive nearly identical benefits. Physics quietly disagrees. The spacecraft travelling faster gains far more orbital energy from the identical burn. The difference can be astonishing. This elegant relationship is known as the Oberth effect, named after Hermann Oberth, one of the pioneers of modern astronautics. During the 1920s, while much of rocketry still belonged more to imagination than engineering, Oberth recognized a subtle truth hidden inside orbital mechanics. A rocket engine produces its greatest long-term benefit when fired at the point of maximum velocity. The engine is not more powerful. The fuel is not more energetic. Instead, the spacecraft's enormous existing speed allows every additional meter per second to generate disproportionately greater orbital energy. It is rather like adding a small push to a bicycle already racing downhill. The push itself is modest. Its consequences become surprisingly large. For decades, this principle appeared primarily in textbooks and mission analyses. Space agencies occasionally used it during planetary encounters, but never on the extraordinary scale now being proposed for the Interstellar probe. The new mission asks an audacious question. What if the spacecraft could approach the Sun more closely than any deep space explorer before it? What if it delayed its most important engine burn until the precise instant when its velocity reached its absolute maximum? Could the Sun itself become the ultimate gravitational slingshot? The calculations suggest that it can. In one proposed trajectory, the spacecraft first departs Earth aboard a heavy launch vehicle before using Jupiter to reshape its orbit. Rather than continuing outward, Jupiter redirects the probe inward, sending it toward an extraordinarily close solar encounter. Closer than Mercury, closer than any planet, within only a few solar radii of the visible surface. There, gravity accelerates the spacecraft to breathtaking speed. Only then does the critical maneuver begin. At the moment of closest approach, while the spacecraft races through the deepest part of the Sun's gravitational well, its propulsion system ignites. The burn itself may last only minutes. Its consequences endure for decades. Instead of escaping the Sun at speeds comparable to Voyager, the spacecraft could depart at velocities approaching 20 astronomical units each year. To appreciate that figure, it helps to compare it with familiar missions. Voyager 1 currently travels outward at roughly 3.5 astronomical units per year. The proposed Interstellar probe could move 5 or 6 times faster. A distance that required Voyager nearly half a century might be reached within little more than a decade. The outer heliosphere would no longer represent the distant horizon of an entire scientific career. It would become an early milestone. Such speed changes more than travel time. It changes the questions scientists can realistically ask. In previous generations, many deep space investigations demanded patience extending across several lifetimes. Engineers designed spacecraft knowing that the most distant discoveries might arrive long after their own work had ended. A faster mission compresses those timescales. Researchers who helped design the spacecraft may also analyze the data returned from its earliest encounters with interstellar space. Exploration becomes more immediate. Yet extraordinary opportunities rarely arrive without extraordinary challenges. Approaching so close to the Sun means entering an environment unlike anything encountered by the Voyagers. Sunlight becomes overwhelming. Heat intensifies to levels capable of destroying conventional materials. Radiation grows relentless. The spacecraft must survive conditions under which many familiar metals would weaken, electronics would fail, and unprotected instruments would quickly become unusable. The Oberth maneuver is therefore not simply a triumph of orbital mechanics. It is also a test of material science, thermal engineering, and spacecraft design operating together at the limits of present technology. The equations describing the trajectory are remarkably well understood. Whether humanity can build a machine capable of executing that trajectory remains the far more difficult question. And that question leads directly to the greatest engineering challenge facing the entire mission. How do you build a spacecraft that can safely touch the edge of the sun without becoming part of it? The mathematics behind the Oberth maneuver is surprisingly straightforward. The engineering required to perform it is anything but. On paper, the idea almost seems too elegant to be real. A spacecraft falls toward the sun, reaches extraordinary speed, ignites its engine at precisely the right moment, and departs the solar system carrying far more energy than the same engine could ever provide elsewhere. The equations are well understood. Physicists have trusted them for generations. Yet there is a profound difference between understanding an equation and asking a spacecraft to live inside it. Every mission that ventures into deep space must solve a familiar collection of problems. Power, navigation, communication, reliability. The Interstellar probe must solve all of these while also surviving one of the harshest environments any spacecraft has ever intentionally entered. Its greatest obstacle is not distance, it is heat. The sun appears gentle from Earth because our planet orbits at an extraordinarily comfortable distance of about 1 astronomical unit, nearly 150 million kilometers away. At that range, sunlight warms oceans, powers weather, and makes life possible. Move inward, however, and the character of sunlight changes with startling speed. Mercury, orbiting less than half Earth's distance from the sun, receives roughly 7 times more solar energy than our planet. The Parker Solar Probe, during its closest approaches, experiences hundreds of times more solar radiation than Earth ever does. The proposed interstellar probe would venture into a similarly unforgiving environment if the full Solar Oberth trajectory is selected. Here, sunlight ceases to feel like warmth. It becomes an engineering problem measured in kilowatts per square meter. Every exposed surface absorbs tremendous amounts of energy. Without protection, structural materials would rapidly overheat. Sensitive electronics would fail. Optical instruments could become permanently damaged. Even tiny imperfections in thermal shielding might gradually grow into catastrophic weaknesses. Unlike the cold emptiness that people often associate with space, the region close to the sun is dominated by overwhelming energy. Survival depends not upon generating heat, but upon refusing to absorb it. That requirement has transformed heat shields into one of the defining technologies of modern space exploration. A casual observer might imagine a heat shield as little more than a thick protective plate. The reality is considerably more sophisticated. Modern thermal protection systems are designed to reflect, absorb conduct, and radiate heat in carefully controlled ways. Every layer performs a different task. Some materials reflect incoming sunlight. Others prevent heat from reaching internal structures. Still others slowly release absorbed energy back into space through infrared radiation. The challenge is not merely resisting high temperatures. It is maintaining stability for years afterward. A spacecraft that survives its closest solar approach but suffers hidden structural damage may fail decades later in deep interstellar space. Engineers therefore design for longevity rather than survival alone. The Parker Solar Probe demonstrated what becomes possible when materials science reaches extraordinary levels of precision. Its carbon composite heat shield, only a few centimeters thick, protects the spacecraft while the sun-facing surface reaches temperatures exceeding 1000 degrees Celsius. Behind that shield, many onboard systems remain near room temperature. The contrast is almost difficult to believe. One side glows beneath the fiercest sunlight ever encountered by a human spacecraft. Only a short distance away, delicate electronics continue operating normally. This achievement represents far more than clever engineering. It provides confidence. Before Parker flew, many thermal models remained exactly that. Models. Now researchers possess years of real observations describing how advanced materials behave during repeated close solar encounters. The sun itself has become a laboratory. Those lessons extend well beyond heat shields. Solar radiation influences electrical systems. High-energy particles gradually alter electronic components. Tiny sensors accumulate damage over time. Mechanical structures expand and contract as temperatures fluctuate. Every subsystem aboard the spacecraft experiences stresses unlike those encountered in the colder outer solar system. The closer engineers examine the problem, the more interconnected every decision becomes. A stronger heat shield increases protection. It also increases mass. Greater mass demands additional launch energy. Additional launch energy may require a larger rocket. A larger rocket influences mission cost. Mission cost affects political approval. Even a single engineering improvement can ripple through the entire project. This constant balancing of competing priorities defines spacecraft design. There is rarely a perfect solution, only the most effective compromise. Power presents another equally fascinating challenge. The Voyager spacecraft relied upon radioisotope thermoelectric generators fueled by plutonium. 238 producing electricity steadily for decades as radioactive decay released heat. That remarkable technology has allowed the Voyagers to continue operating nearly half a century after launch. The Interstellar probe is expected to require an equally reliable source of long-term power. Unlike spacecraft operating near Earth, it cannot depend upon solar panels. Ironically, although the mission approaches extremely close to the Sun during one brief phase, its true destination lies where sunlight becomes almost unimaginably weak. Hundreds of astronomical units from the Sun, even enormous solar arrays, would generate only tiny amounts of electricity. The spacecraft must therefore carry its own energy source across half a century of exploration. Communication presents still another quiet challenge. Signals travel at the speed of light, yet even light requires many hours to cross the immense distances involved. Commands sent from Earth cannot guide the spacecraft moment by moment. By the time a radio message arrives, the critical maneuver will already have finished. The spacecraft must navigate largely on its own. Its guidance software becomes in effect another member of the mission team. Autonomy has gradually become one of the defining characteristics of deep space exploration. The farther humanity reaches into the solar system, the more responsibility must be entrusted to machines operating alone. Perhaps this is one of the most remarkable aspects of the Interstellar probe. Its success depends not upon one revolutionary invention, but upon the quiet convergence of many different technologies. Advanced materials, long-lived power systems, autonomous navigation, precision propulsion, high-performance communications. Each has matured separately over decades. Together they may finally make possible a journey that would have been unimaginable when Voyager first departed Earth. And if all of those systems perform exactly as intended, the reward will not simply be a faster spacecraft. It will be the opportunity to cross a boundary that humanity has touched only twice, before carrying instruments capable of revealing that frontier in unprecedented detail. For beyond the fierce light of the Sun lies an invisible frontier that has shaped our solar system for billions of years, yet remains one of the least understood regions in our cosmic neighborhood. The boundary between the solar system and interstellar space is often described as though it were a line, a frontier, a border, something a spacecraft crosses in a single dramatic moment before leaving one realm and entering another. Reality is quieter. Like many boundaries in nature, it is not a wall but a transition. The Sun continuously releases an immense stream of charged particles known as the solar wind. These particles flow outward in every direction at hundreds of kilometers per second, carrying with them the Sun's magnetic field. For billions of years, this invisible wind has carved out a vast cavity within the surrounding galaxy. That cavity is called the heliosphere. Earth, Mars, Jupiter, Neptune, and every planet we know resides safely inside it. From our everyday perspective, the heliosphere feels limitless. In truth, it is simply a bubble. An enormous one, certainly stretching well beyond the orbit of Pluto, but still only a tiny structure drifting through the much larger environment of the Milky Way. Outside that bubble lies the local interstellar medium. It is not empty, far from it. The space between stars contains thin clouds of gas, microscopic grains of dust, magnetic fields and high-energy particles traveling across the galaxy. The density is extraordinarily low by earthly standards, yet over astronomical distances it shapes entire stellar systems. For decades, astronomers could only estimate how these two environments interacted. The solar wind rushed outward. The interstellar medium pressed inward. Somewhere between them a delicate balance emerged. Where exactly that balance occurred remained uncertain. The Voyagers eventually provided humanity's first direct encounter with that frontier. Voyager 1 crossed the heliopause in 2012. Voyager 2 followed in 2018. These milestones represented historic moments, but they also revealed an unexpected limitation. Humanity possesses only two measurements. Imagine attempting to understand the shape of an entire ocean coastline after standing on only two small beaches separated by thousands of kilometers. You would certainly learn something valuable. You would not learn the whole story. The heliosphere surrounds the solar system in every direction. Its structure responds to the changing activity of the sun, the pressure of the surrounding interstellar medium, and magnetic fields extending across enormous regions of the galaxy. Two crossings cannot fully describe such a dynamic system. They offer clues, not certainty. This realization lies at the heart of the Interstellar probe's scientific purpose. Its mission is not simply to cross the heliopause. Its mission is to study it. That distinction may sound subtle, yet it completely changes the spacecraft's priorities. Voyager reached the boundary with instruments designed during the early 1970s. Those instruments performed magnificently, exceeding every reasonable expectation. Even so, they reflected the technological limits of their era. Their detectors possessed sensitivities unimaginable at the time, but modest by modern standards. Their computers processed only tiny amounts of information. Their communication system returned precious data at astonishingly low transmission rates compared with today's capabilities. Half a century of scientific progress has transformed what researchers can now measure. Modern magnetometers can detect variations in magnetic fields with extraordinary precision. Particle detectors distinguish subtle differences in energy that earlier generations could barely observe. Mass spectrometers identify the chemical composition of individual particles passing through space. Sensitive plasma instruments measure the behavior of electrically charged gases in remarkable detail. Collectively, these technologies allow scientists to observe the invisible environment surrounding the spacecraft with clarity impossible during the Voyager era. Instead of asking only where the heliosphere ends, researchers can begin asking far richer questions. How does the interstellar magnetic field bend around the solar system? Does the heliosphere remain stable over decades, or does it continuously change shape? How efficiently does it shield the planets from incoming cosmic radiation? How do energetic particles travel across its boundaries? Each answer reveals something not only about our own solar system, but about every planetary system throughout the galaxy. Stars do not exist in isolation. Each moves through the Milky Way surrounded by its own stellar wind interacting with the surrounding interstellar environment. By understanding our own heliosphere, astronomers gain a template for understanding countless others. Perhaps the most fascinating question concerns the shape of the heliosphere itself. For many years, textbooks often illustrated it as something resembling a comet. The sun moving through the galaxy produced a rounded front while a long tail stretched behind. The image felt intuitive. A boat moving through water creates a wake. Surely the solar system should do something similar. Yet modern computer simulations have challenged that familiar picture. Some researchers now propose that the heliosphere may resemble something quite different. Instead of a long trailing tail, magnetic fields generated by the solar wind may create two broad lobes extending outward, giving the overall structure a shape that has been compared somewhat playfully to a croissant. Neither model has been conclusively confirmed. Both remain grounded in serious scientific work. What matters is not which illustration appears more attractive. What matters is that scientists genuinely do not yet know. This uncertainty is not a weakness. It is precisely why exploration continues. Only direct measurements from new locations can distinguish between competing models. The Interstellar probe offers something uniquely valuable. After crossing beyond the heliosphere, it will gradually increase its distance while continuously observing the solar system from outside its protective bubble. For the first time, humanity may obtain a truly global perspective, not a computer reconstruction, not an inference based upon limited data, but observations collected from a vantage point no spacecraft has previously occupied for such an extended period. It is a remarkable reversal of perspective. Throughout history, astronomers have looked outward from Earth toward the universe. This mission proposes looking inward from interstellar space toward home. Sometimes understanding a place requires leaving it. Sometimes the clearest view of a forest comes only after walking beyond its edge. If the interstellar probe succeeds, humanity may finally see its own cosmic neighborhood as it truly appears within the larger galaxy. And once that new perspective becomes possible, another extraordinary opportunity quietly emerges. The journey beyond the heliosphere is not empty. Between the planets and the stars lies an unexplored frontier filled with ancient worlds, drifting dust, invisible radiation, and clues to the earliest history of the solar system itself. By the time the interstellar probe leaves the heliosphere behind, one remarkable chapter of its journey will have ended. Another, perhaps even more important one, will quietly begin. The popular image of deep space often suggests endless emptiness. Vast black distances separate the stars, interrupted only by the occasional wandering comet or distant planet. It is an understandable impression. Space appears almost perfectly dark, and the distances involved are so enormous that the regions between the planets seem insignificant. Yet appearances can be deceptive. The outer solar system is not empty. It is simply subtle. Long before a spacecraft reaches the true interstellar medium, it must travel through one of the least explored regions humanity has ever encountered. Beyond Neptune stretches the Kuiper Belt, an immense population of icy bodies left behind from the earliest days of planetary formation. Farther still may lie the distant Oort cloud, a vast spherical reservoir of frozen objects extending perhaps tens of thousands of astronomical units from the Sun. These regions preserve a record of the solar system's childhood. Unlike Earth, whose surface has been reshaped by oceans, weather, and plate tectonics, many distant icy bodies have remained remarkably unchanged for more than 4 billion years. They are not geological museums in the ordinary sense. They're fragments of the original material from which the planets themselves emerged. Every one of them contains a piece of our history. The difficulty is that very few have ever been examined closely. Pluto received its first close visit only in 2015, when the New Horizons spacecraft revealed a world far more dynamic than anyone expected. Instead of a frozen relic, scientists discovered towering mountains of water, ice, vast plains of nitrogen glaciers, and evidence suggesting that internal geological activity had continued much longer than anticipated. Pluto taught an important lesson. Distance does not imply simplicity. If one small world at the edge of the solar system could overturn decades of assumptions, what surprises might await among the hundreds of other large Kuiper Belt objects that have never been visited? The interstellar probe may provide part of that answer. Although its primary objective lies far beyond the planets, mission planners have explored trajectories that could bring the spacecraft close to one or more distant icy worlds during its outward journey. Which object ultimately becomes accessible depends upon the final launch date and trajectory, since these bodies are themselves moving steadily along their slow orbits around the Sun. Among the possibilities are objects such as Quaoar and Orcus worlds that, until recently, were little more than faint points of light in powerful telescopes. Quaoar, orbiting at roughly 43 astronomical units from the Sun, surprised astronomers when observations revealed a delicate ring system surrounding it. According to conventional expectations, those rings should not remain stable where they are observed today. Their existence suggests that the dynamics of small icy worlds may be more complicated than current theories predict. Even seemingly quiet objects continue to challenge familiar ideas. Orcus presents another intriguing case, sometimes described as the anti-Pluto because of the relationship between its orbit and that of Neptune. It possesses its own substantial moon and may preserve clues about the violent gravitational interactions that shaped the outer solar system billions of years ago. A single close flyby of either world would produce a scientific return comparable to entire planetary missions of previous decades. Yet these encounters represent only a small portion of the journey. The true scientific richness lies in the space between the worlds. Every hour, microscopic grains of interstellar dust pass silently through the solar system. Most are far smaller than the grains of sand. Individually, they appear insignificant. Collectively, they carry information from ancient stellar explosions, dying stars and clouds where new suns are still forming. They are travelers from environments no spacecraft has yet visited. By analysing their composition, scientists can reconstruct aspects of the chemical history of our galactic neighbourhood. The Interstellar probe is expected to carry instruments capable of studying these particles one by one. Each tiny grain becomes a messenger. Some formed before our sun was born. Others originated in distant stellar systems whose name humanity will never know. Together they reveal that the solar system has never been isolated. It continuously exchanges matter with the wider galaxy. Charged particles tell an equally fascinating story. Cosmic rays constantly stream through interstellar space at extraordinary energies. Some originate in exploding supernovae. Others may come from extreme environments surrounding neutron stars or even supermassive black holes. Their precise origins remain one of astrophysics' enduring mysteries. Fortunately for life on Earth, much of this radiation is deflected by the heliosphere. The solar system's protective bubble acts as a partial shield, reducing the number of energetic particles reaching the inner planets. But how effective is that shield? Does its protective ability change as solar activity rises and falls? How do cosmic rays interact with the heliopause itself? The Voyagers provided the first tantalizing hints. The Interstellar probe could transform those hints into detailed measurements, collected continuously over decades. This knowledge extends well beyond curiosity. Future human exploration beyond the solar system will depend upon understanding the radiation environment through which spacecraft and one day perhaps crews must travel. The invisible becomes practical. The distant becomes personal. Even the faint plasma filling interstellar space possesses its own quiet story. Although extraordinarily thin, this ionized gas carries magnetic fields across vast regions of the galaxy. Tiny oscillations ripple through it like waves crossing an invisible ocean. Sensitive instruments can detect these subtle vibrations, allowing scientists to infer properties of the surrounding medium that cannot be observed directly. Listening to space in this sense becomes another way of seeing it. Every measurement collected during the journey outward contributes to a broader picture, not simply of our solar system, but of its relationship with the Milky Way itself. Gradually, a remarkable realization emerges. The Interstellar probe is not merely leaving home, it is becoming the first spacecraft specifically designed to explore the environment that connects every star to every other star. And as scientists began contemplating such ambitious journeys, another extraordinary idea emerged alongside it. If a spacecraft could travel hundreds of astronomical units away from the Sun, perhaps it could do something even more astonishing than study interstellar space. Perhaps it could use the Sun itself as the largest telescope nature has ever created. For centuries, every telescope humanity has ever built has shared one unavoidable limitation. No matter how large its mirror, no matter how sensitive its detectors, every telescope observes the universe from almost exactly the same place. Whether it stands on a mountain in Chile, circles Earth aboard a satellite, or drifts quietly near the second Lagrange point alongside the James Webb Space Telescope, the difference is almost insignificant when measured against the scale of the galaxy. All of our observatories remain clustered within a tiny neighbourhood surrounding the Sun. The Interstellar probe suggests a subtle but profound change in perspective. Instead of building a larger telescope, perhaps we should move the observer itself. That simple shift opens possibilities that would otherwise remain forever inaccessible. As the spacecraft journeys hundreds of astronomical units away from the Sun, it enters a region where the solar system begins to reveal itself from an entirely unfamiliar direction. Throughout history, astronomers have looked outward. For the first time, a scientific observatory could spend decades looking homeward. This reversal may sound philosophical. In reality, it is one of the mission's greatest scientific strengths. Every photograph of Earth taken from deep space has transformed the way humanity sees itself. The famous image known as the pale blue dot captured by Voyager 1 in 1990 from nearly 6 billion kilometers away reduced our entire civilization to a tiny point of light suspended in a sunbeam. Carl Sagan reflected that every king, every farmer, every child, every explorer, and every dreamer had lived upon that nearly invisible pixel. The image changed nothing about Earth itself. It changed us. Perspective has a remarkable ability to reshape understanding. The Interstellar probe extends that idea far beyond a single photograph. Instead of viewing only Earth, scientists hope to observe the solar system's entire protective environment from outside. This environment, the heliosphere, has never been seen as a complete structure. Its existence is inferred from measurements. Its boundaries are reconstructed through models. Its overall shape remains debated. Imagine trying to understand the form of a great cathedral while standing inside it. You may carefully examine the walls. You may measure the columns. You may even map individual rooms with extraordinary precision. Yet the complete architecture remains hidden until you step outside. Only then does the design become visible. The heliosphere presents a similar challenge. For decades, spacecraft have measured individual regions from within. Pioneer ventured outward. Voyager crossed the boundary. New Horizons continues its quiet journey through the outer solar system. Together they provide valuable observations, but all remain or remained for most of their missions inside the very structure they sought to understand. The Interstellar probe changes the geometry. By travelling far beyond the heliopause while continuing to observe inward, it gains an entirely different vantage point. From there, scientists hope to answer questions that have resisted decades of investigation. Does the heliosphere possess a long comet-like tail stretching behind the Sun as it moves through the galaxy? Or is its shape controlled primarily by magnetic forces producing two broad lobes rather than one extended wake? Computer simulations support both possibilities under different assumptions. Neither has yet received decisive observational confirmation. Direct measurements from outside the heliosphere may finally distinguish between them. The implications extend far beyond cartography. The heliosphere acts as Earth's first line of defense against galactic cosmic rays. Its magnetic fields influence how energetic particles enter the solar system. Its changing structure responds to variations in solar activity and to conditions within the surrounding interstellar cloud. Understanding its geometry, therefore, improves our understanding of the radiation environment experienced by every planet orbiting the Sun. It also offers clues about countless other stars. Astronomers now know that planets are common throughout the Milky Way. Thousands of exoplanets have already been discovered. Many orbit stars remarkably similar to our own. If the Sun produces a heliosphere, then other stars almost certainly generate analogous stellar bubbles. Some may be larger, some smaller. Some may offer stronger protection against cosmic radiation. Others may expose their planets to a far harsher galactic environment. By understanding our own heliosphere in detail, scientists gain a framework for interpreting planetary systems across the galaxy. In this way, a mission focused on our immediate surroundings quietly becomes relevant to the broader search for habitable worlds. The closer researchers examine the problem, the more interconnected everything appears. The solar wind shapes the heliosphere. The heliosphere regulates cosmic radiation. Cosmic radiation influences planetary atmospheres. Planetary atmospheres affect the long-term evolution of life. A question that begins with the edge of the solar system gradually reaches into one of astronomy's oldest mysteries. Why do some worlds remain suitable for life while others do not? The Interstellar probe cannot answer that question directly, but it can improve one important piece of the puzzle. Meanwhile, the spacecraft's journey continues. Each passing year carries it farther from the Sun. Communication delays steadily increase. Sunlight fades until even the brightest star in our sky becomes only another brilliant point among many. Yet something remarkable happens as distance grows. The farther the spacecraft travels, the more valuable its observations become. Near Earth, many measurements are influenced by the constantly changing environment of the inner solar system. Far beyond the heliosphere, those local disturbances gradually disappear. The galaxy itself begins to dominate. The spacecraft enters a region where interstellar conditions can finally be studied on their own terms, rather than through the filtering influence of the Sun. In a sense, the Interstellar probe becomes humanity's first permanent scientific outpost in the space between stars. Not a visitor passing briefly through, a resident. That distinction carries enormous scientific promise. It also inspires another, even more ambitious possibility. If engineers can successfully send spacecraft hundreds of astronomical units from the Sun, perhaps those distant observatories need not study only our own solar system. Perhaps they can transform the Sun itself into an instrument capable of revealing distant Earth-like planets in astonishing detail. What sounds almost impossible turns out to emerge naturally from one of the oldest predictions of Einstein's theory of general relativity. It is one of the quieter predictions in modern physics. Unlike black holes or expanding galaxies, it rarely appears in popular discussions of astronomy. There are no dramatic explosions, no violent collisions, no dazzling images captured by giant observatories. Instead, it begins with a simple observation. Gravity bends light. When Albert Einstein completed the general theory of relativity in 1915, one of its remarkable consequences was that mass does more than attract other masses. It also changes the geometry of space itself. Light, although massless, must travel through that curved geometry. As a result, its path bends. The effect is extraordinarily small under ordinary circumstances. A passing beam of starlight shifts by only a tiny angle as it grazes the Sun. Detecting that shift required careful observations during a total solar eclipse, only a few years after Einstein published his theory. Yet the principle behind it is profound. If gravity bends light, then sufficiently massive objects begin to behave in a limited sense like lenses. Not lenses made of glass, lenses made of space-time itself. Astronomers now observe this phenomenon throughout the universe. Massive galaxies distort the appearance of even more distant galaxies behind them. Clusters of galaxies magnify objects so remote that no ordinary telescope could detect them. Sometimes gravity stretches background galaxies into graceful arcs. Sometimes it produces multiple images of the same object. Occasionally it creates nearly perfect circles of light known as Einstein rings. These observations have become routine tools of modern cosmology. Yet hidden within the mathematics lies an extraordinary possibility much closer to home. The Sun itself is also a gravitational lens. Unlike distant galaxy clusters, however, it is close enough that humanity might someday place a spacecraft at precisely the right location to use this natural optical system. The required distance is astonishing, roughly 550 astronomical units from the Sun, far beyond Pluto, far beyond the heliopause, far beyond where any dedicated scientific observatory has ever operated. Coincidentally, this is almost exactly the region toward which the Interstellar probe is already intended to travel. Here the story begins to connect in unexpected ways. Originally, these ideas developed as separate mission concepts. The Interstellar probe focuses on heliophysics and the local interstellar medium. The Solar Gravitational Lens mission pursues an entirely different objective. Yet both require humanity to master the same fundamental challenge, travelling enormous distances from the Sun within practical timescales. Solve one problem and the other becomes dramatically more achievable. The physics of the solar gravitational lens is surprisingly elegant. Suppose a distant Earth-like planet happens to lie almost perfectly behind the Sun from the spacecraft's perspective. As light from that planet passes the Sun, gravity bends its path inward. Instead of spreading uniformly through space, the light becomes concentrated along a long focal region extending outward, beyond approximately 550 astronomical units. A spacecraft positioned within that region receives far more light than it otherwise would. The Sun itself becomes the telescope, not metaphorically, literally. Unlike any telescope humanity could realistically build, this gravitational lens possesses an effective aperture measured not in meters, but in hundreds of thousands of kilometers. No manufactured mirror approaches such a scale. The amplification is extraordinary. Calculations suggest that the brightness of a distant target could increase by factors approaching 100 billion. At first, such numbers seem almost unbelievable, yet they arise directly from Einstein's equations, which have successfully described gravitational lensing throughout the observable universe for more than a century. Of course, every remarkable opportunity introduces equally remarkable complications. The spacecraft would not simply point a camera toward the target planet and capture a familiar photograph. Gravity does not produce an ordinary image. Instead, light from the distant world forms a thin ring surrounding the Sun. Every tiny section of that ring contains information from different regions of the planet's surface. Recovering the complete image requires patience. The spacecraft must move carefully through the focal region while recording countless measurements. Sophisticated reconstruction algorithms then combine those observations into a detailed map. Rather than taking a photograph in a single instant, scientists gradually assemble one over months or even years. The process resembles building a mosaic from millions of tiny pieces. The reward could be extraordinary. Current telescopes generally detect exoplanets as unresolved points of light. Astronomers infer their atmospheres from subtle changes in spectra. They estimate temperatures. They estimate sizes. Sometimes they detect clouds. Direct surface details remain beyond the reach of existing technology. A solar gravitational lens mission changes that possibility. Instead of observing a single pixel, researchers may eventually resolve continents, oceans, and large-scale weather systems on distant Earth-sized planets orbiting nearby stars. Not through speculation, through direct imaging. The prospect remains one of the most ambitious ideas in all of astronomy, yet it rests upon the same quiet foundation as the Interstellar probe. Distance. Everything depends upon reaching the outer solar system quickly enough to make such missions practical within a human lifetime. The farther scientists think ahead, the more clearly they recognize that interstellar exploration is no longer about one spacecraft. It is about building an entirely new infrastructure of knowledge. The Interstellar probe maps the frontier. Future missions exploit it. One generation discovers the road. The next travels farther along it. This gradual expansion has defined exploration throughout human history. Coastlines gave way to oceans. Oceans gave way to continents. Continents eventually led to the sky. Now the edge of the heliosphere may become the next familiar landmark from which even greater journeys begin. Curiously, however, amid all these discussions of propulsion optics and interstellar science, another question quietly persists. If humanity does send another spacecraft into the deep darkness between the stars, what should it carry with it? Not as an instrument, not as an experiment, but as a message. Long before Voyager ever left Earth, its creators understood that the mission was about more than science. The spacecraft would measure magnetic fields, photograph distant planets, and study invisible streams of charged particles. Yet someone asked a question that had nothing to do with engineering. If this machine survives longer than humanity remembers building it, should it carry something that speaks for us? The answer became one of the most quietly beautiful decisions in the history of exploration. Attached to the side of each Voyager spacecraft is a gold-plated copper phonograph record. It is not especially large. Its weight is almost insignificant compared with the spacecraft itself. Its scientific value is essentially zero, and yet it has become one of the most enduring symbols of the entire mission. Known simply as the Golden Record, it contains music greetings, photographs, and natural sounds collected from Earth in 1977. There are recordings of ocean waves, birds singing, footsteps, laughter, and a mother's first words to her newborn child. There are greetings spoken in dozens of languages. There is music composed centuries apart from Johann Sebastian Bach to Chuck Berry. Taken together, the collection is neither complete nor perfect. It was never intended to be. Instead, it represents a snapshot, a brief portrait of one civilization during one particular moment in cosmic history. Carl Sagan and the committee responsible for assembling the record understood the impossibility of the task before them. How does an entire planet introduce itself? No selection could ever satisfy everyone. Every choice meant another would be left behind. Should the record emphasize science, music, history, languages, nature, human emotion? The committee debated these questions intensely, not because they expected the record to be discovered, but because the process itself forced humanity to ask what it valued most. In the end, they accepted that perfection was impossible. Authenticity mattered more. The record also carries instructions explaining how it should be played engraved directly onto its protective cover. Nearby is one of its most elegant features, a pulsar map that identifies the Sun's location relative to 14 rapidly rotating neutron stars. Each pulsar flashes at a unique rhythm, creating a kind of cosmic address that remains recognizable across immense spans of time. Even if continents disappear and civilizations change, those pulsars will continue marking our place within the galaxy. It is a remarkable mixture of poetry and precision. The Golden Record does not simply say who we are, it explains where we came from. Nearly 50 years have now passed since those records began their silent journey toward interstellar space. Humanity has changed enormously during that time. When Voyager launched, the personal computer was still a novelty. The internet did not yet connect the world. No one had confirmed a single planet orbiting another sun. Black holes remained largely theoretical objects in the public imagination. Artificial intelligence belonged mostly to speculative fiction. The human genome had not been sequenced. Thousands of exoplanets remained undiscovered. The universe described by astronomy in 1977 was in many ways far smaller than the one we know today. That raises an unexpectedly difficult question. If the interstellar probe eventually flies, should it carry a new message? Officially, the current mission concept contains no modern equivalent of the Golden Record. The reasons are practical rather than philosophical. Every additional gram increases launch mass. Every additional subsystem introduces complexity. The mission exists first and foremost to conduct science. Even so, the discussion returns whenever scientists, engineers, and the public gather to talk about humanity's next great journey beyond the solar system. Not because another message is technically necessary, because it feels culturally significant. If Voyager captured Earth in 1977, what would represent Earth in the 21st century, the possibilities have expanded almost beyond comprehension. Modern storage technologies can preserve astonishing quantities of information in remarkably small volumes. Researchers have demonstrated methods of recording hundreds of terabytes with endurable materials such as fused quartz. Unlike magnetic disks or ordinary optical media, these storage systems may remain readable for extraordinarily long periods under the right conditions. A storage device no larger than the palm of a hand could contain more information than entire national libraries once held. It could preserve every major language, complete collections of literature, scientific knowledge accumulated across generations, music from every culture, maps of Earth's ecosystems, medical discoveries, mathematics, art, the history of human exploration, even the original Golden Record itself. Technically, humanity could now send not merely a greeting but an archive, yet abundance creates its own dilemma. When everything can be included, what deserves emphasis? Should the message celebrate technological achievement? Should it focus instead upon ordinary human experience? Would a photograph of Earth's forests speak more eloquently than engineering diagrams? Would recordings of children laughing convey more than encyclopedias ever could? These questions possess no scientific answers. They belong equally to philosophers, artists, historians, and every person who calls Earth home. Perhaps that is why they remain so compelling. They remind us that exploration has always involved more than discovering new places. Every expedition also reveals something about the travelers themselves. The Voyagers did not merely transform planetary science. They became mirrors in which humanity examined its own identity. The interstellar probe may eventually do the same. By asking what message should accompany such a mission, we are quietly asking another question. What kind of civilization are we becoming? One defined only by technology, or one that still believes knowledge, curiosity, beauty and memory deserve a place aboard even our most ambitious scientific machines? The answer may never appear in a technical report. Yet it could shape one of the smallest, quietest, and most meaningful components of the spacecraft. Because long after its instruments finish measuring magnetic fields and interstellar plasma, long after its transmitters eventually fall silent, whatever message it carries may continue drifting through the galaxy for millions of years. And before any of that can happen, humanity must overcome a challenge far more familiar than gravity engineering or deep space. It must first decide whether such a journey is worth beginning at all. Every ambitious scientific mission eventually reaches a point where engineering is no longer the greatest uncertainty. The mathematics has been checked, the trajectories have been simulated, the instruments have been refined. Researchers understand, at least in broad terms, what must be built. The remaining question becomes something far less predictable. Will society choose to build it? The history of space exploration is filled with missions that never flew, Some existed only as sketches in laboratory notebooks. Others progressed through years of careful engineering before changing political priorities quietly brought them to an end. Unlike the laws of physics, national budgets are rarely stable. Scientific opportunity does not always arrive at the same moment as political willingness. The Interstellar probe finds itself at precisely this crossroads. After more than a decade of technical studies, the mission has matured into one of the most carefully examined concepts for deep space exploration. Researchers have investigated trajectories, communication systems, thermal protection, scientific instruments, and long-term power generation. Independent specialists have evaluated many of its central assumptions. The mission is no longer waiting for someone to discover whether it is physically possible. It is waiting for someone to decide that it matters. That distinction is important. People sometimes imagine that the greatest barrier to exploring the universe is ignorance. More often it is patience. Large scientific missions unfold across timescales that rarely match political cycles. Governments typically think in terms of years. Major space missions often think in terms of decades. An engineer who joins a project shortly after graduating from university may reach retirement before the spacecraft completes its primary mission. The rewards arrive slowly. The investments arrive immediately. This has always been one of the quiet tensions within scientific exploration. Voyager itself almost failed to reach the launch pad. During the early planning stages, NASA envisioned a far more ambitious grand tour involving 4 spacecraft. Budget reductions steadily narrowed those ambitions until only 2 vehicles remained. Even those survived only after years of negotiation, redesign, and careful justification. Looking back today, it is difficult to imagine planetary science without Voyager. At the time, however, its future was anything but certain. History repeated itself in different forms with many later missions. The Hubble Space Telescope spent years overcoming technical setbacks before transforming modern astronomy. The Cassini mission to Saturn required decades of international cooperation before finally departing Earth. The James Webb Space Telescope endured repeated delays, redesigns, and escalating costs that led many observers to wonder whether it would ever launch at all. Yet once these observatories began returning data, they fundamentally reshaped humanity's understanding of the universe. Exploration often asks for confidence long before it offers proof. The Interstellar probe belongs to this same tradition. Unlike missions focused on nearby planets, its scientific goals cannot easily be compressed into a few years. Its greatest discoveries may emerge 20 or 30 years after launch. Some observations may continue for half a century or longer. Such timescales require an unusual form of optimism. Scientists designing the spacecraft today understand that many of the mission's most valuable measurements may be analysed by researchers who are still students today, or perhaps children. In few other professions do people knowingly devote decades to work whose greatest rewards will belong largely to others. There is something deeply human about that willingness. Cathedrals took generations to build. Ancient observatories were constructed by people who knew they would never witness every discovery made within them. Libraries preserve knowledge for readers yet unborn. The Interstellar probe belongs to that same family of long-term endeavours. It is an investment in curiosity across generations. The financial challenges, however, remain substantial. Deep space exploration is inherently expensive. Launch vehicles must deliver spacecraft beyond Earth's gravity. Long-lived power systems require years of development. Scientific instruments undergo exhaustive testing to ensure they continue functioning after decades in space. Communication networks capable of receiving faint signals across hundreds of astronomical units demand continual maintenance. Every component reflects years of specialized work performed by thousands of individuals. Critics sometimes ask whether such investments are justified. Could those resources be directed elsewhere? The question deserves thoughtful consideration. Scientific exploration has never existed outside broader society. Its value cannot be measured only in photographs or scientific papers. History suggests that ambitious exploration produces consequences extending far beyond its original objectives. Technologies developed for space missions frequently find applications in medicine, communications, materials, science, and countless other fields. More difficult to measure, yet perhaps equally important, is the cultural influence of exploration itself. Every generation benefits from projects that encourage people to think beyond immediate concerns. Spacecraft remind us that civilization is capable of planning for futures extending well beyond the next election, the next economic cycle, or even the next generation. They expand the horizon of human thought. There is another reason the Interstellar probe matters. Its scientific questions cannot be answered from Earth. No telescope, regardless of size, can replace direct measurements made beyond the heliosphere. Some frontiers yield only to observation from within. Others require stepping outside entirely. The boundary between the solar system and interstellar space belongs to the second kind. Eventually someone must go there. Not in person, but through the quiet presence of a carefully built machine carrying humanity's curiosity farther than it has ever travelled before. Whether that machine launches in the late 2030s, the early 2040s, or sometime thereafter, remains uncertain. Schedules change, budgets evolve, priorities shift. Such uncertainty is an ordinary part of large scientific endeavours. The deeper certainty lies elsewhere. The questions themselves are not disappearing. The edge of the heliosphere will remain where it is. The local interstellar cloud will continue surrounding our solar system. The galaxy will patiently wait. Sooner or later, humanity will choose to continue the journey. The only uncertainty is when. And perhaps even more importantly, who will be alive to witness the moment when a new spacecraft finally crosses into the space between the stars and begins sending home observations that no previous generation could ever have imagined. There is a curious pattern that appears throughout the history of exploration. Every time humanity reaches what seems to be the edge of the known world, the horizon quietly moves farther away. The first ocean crossed revealed another coastline. The first mountain climbed exposed another range beyond it. The first photographs of distant planets transformed them from mysterious points of light into worlds filled with still deeper mysteries. Knowledge rarely produces endings. More often it reveals larger beginnings. The Interstellar probe belongs to this tradition. Its purpose is not merely to travel farther than Voyager. Its purpose is to reach a place where entirely new questions become possible. That distinction matters because the spacecraft is not designed simply to accumulate data. It is designed to change perspective. For centuries, astronomy has relied upon observing light that arrives naturally from distant objects. Stars shine, galaxies glow, nebulae scatter radiation across the electromagnetic spectrum. Telescopes patiently collect those ancient photons and reconstruct the story they tell. The Interstellar probe takes a different approach. Instead of waiting for distant light to arrive, it carries instruments directly into an environment that has never been explored with modern technology. It is less like building a better camera. It is more like walking into a landscape that has only ever been viewed from the horizon. The farther the spacecraft travels, the less it resembles every previous planetary mission. Planets eventually disappear behind it. Even the Kuiper Belt grows sparse. The familiar architecture of the solar system slowly dissolves into a vast, almost featureless darkness. Yet appearances remain deceptive. Interstellar space is not empty. It is structured by magnetic fields so enormous that they stretch across light years. Invisible clouds of neutral hydrogen drift between neighbouring stars. Microscopic dust grains forged inside ancient stellar explosions continue their slow journeys across the galaxy. Energetic particles race through this environment at nearly the speed of light. The spacecraft enters an ocean whose currents cannot be seen with human eyes. Understanding that ocean requires extraordinary patience. Unlike planetary flybys where dramatic discoveries may occur over only a few hours, interstellar science unfolds almost imperceptibly. The spacecraft measures. It waits. It measures again. Months become years. Years become decades. Gradually patterns emerge. Tiny changes in magnetic field direction reveal structures extending across billions of kilometers. Subtle variations in particle density expose the boundaries between different interstellar clouds. Almost every discovery depends not upon a single dramatic observation, but upon long sequences of quiet measurements collected with remarkable consistency. This slow rhythm reflects the nature of the environment itself. the galaxy evolves on timescales far longer than human civilization. Its largest structures are measured not in kilometers but in light years. Its motions unfold over millions of years. A spacecraft operating for half a century captures only the briefest moment within that larger story. And yet even that brief moment may transform astronomy. One of the most intriguing questions concerns the cloud through which our solar system is currently travelling. Astronomers call it the local interstellar cloud. Compared with Earth's atmosphere, it is extraordinarily thin. Compared with the near vacuum inside the heliosphere, however, it represents a distinctly different environment. Our solar system has not always occupied this cloud, neither will it remain there forever. As the Sun continues its orbit around the centre of the Milky Way, it slowly passes through different regions of interstellar space. Each possesses its own density, its own magnetic properties, its own population of dust and energetic particles. Over immense spans of time, these changing environments may subtly influence conditions within the heliosphere itself. Some researchers have wondered whether particularly dense interstellar clouds could compress the heliosphere, significantly exposing planets to increased levels of galactic cosmic radiation. Others investigate whether changes in the surrounding interstellar medium leave detectable signatures within geological or climatic records on Earth. At present, these ideas remain subjects of active research. Evidence exists. Complete answers do not. The Interstellar probe could provide critical observations that help distinguish between competing explanations, not because it can solve every mystery by itself, but because it occupies a location where no previous observatory has operated with comparable capabilities. This highlights an important principle in science. Sometimes progress depends not upon building a better instrument. Sometimes it depends upon placing an instrument somewhere entirely new. Astronomy has repeatedly advanced through such changes in perspective. Moving telescopes above Earth's atmosphere eliminated atmospheric distortion. Placing observatories in orbit around the Sun expanded uninterrupted observations. Sending spacecraft to other planets transformed distant worlds into nearby laboratories. The Interstellar probe continues this progression. Its destination becomes its greatest instrument. Distance itself acquires scientific value. The farther the spacecraft travels, the more unique its observations become. Perhaps this is why the mission continues attracting attention despite its extraordinary duration. It is not attempting to repeat familiar science. It seeks observations that simply cannot be made anywhere else. There is something quietly inspiring about that ambition. It accepts that some questions require patience, measured not in weeks or months, but in generations. It assumes that understanding our place within the galaxy is worth waiting for, and in doing so it reminds us that exploration has never been about reaching the nearest destination. It has always been about expanding the boundaries of what humanity is capable of knowing. The farther we travel into interstellar space, the more clearly another realization begins to emerge. This mission is no longer only about understanding the edge of the solar system. It is becoming part of a much larger story. A story about what kind of civilization chooses to build machines, whose greatest purpose is simply to learn what lies beyond the next horizon. There is an old assumption that has quietly followed humanity throughout the history of exploration. We often believe that every great journey has a destination, a mountain summit, a distant continent, a new planet. A spacecraft reaches its target, completes its mission, and the story comes to a satisfying conclusion. The deeper we look into the universe, however, the less true that assumption becomes. Modern astronomy has revealed that discovery is rarely a matter of arriving somewhere. Instead, every destination becomes the starting point for an entirely new set of questions. The Interstellar probe may become one of the clearest examples of this pattern. Crossing the heliopause is not its final achievement. It is the moment when the most valuable science truly begins. That idea represents a profound shift in the philosophy of exploration. For much of the space-age missions were designed around places: Mercury, Venus, Mars, Jupiter, Saturn. The destination itself defined the scientific objective. Interstellar exploration changes that relationship. The destination is no longer a world. It is an environment. A vast region extending between stars filled with invisible structures that connect every stellar system throughout the Milky Way. This subtle difference changes almost everything. Instead of studying one planet's atmosphere or one moon's geology, scientists begin studying the galactic neighborhood itself. The solar system stops feeling isolated. It becomes part of a much larger ecosystem. That realization carries consequences reaching far beyond heliophysics. Every star produces a stellar wind. Every star interacts with the interstellar medium. Every planetary system exists inside its own protective bubble shaped by local magnetic fields and the surrounding galaxy. Some stars are far more active than our Sun. Young stars often produce violent eruptions capable of stripping planetary atmospheres. Red dwarf stars can bombard nearby planets with powerful flares for billions of years. Massive stars generate winds so intense that they reshape entire regions of interstellar space. Understanding our own heliosphere therefore provides something invaluable, a reference point. Without knowing how our solar system behaves, it becomes far more difficult to interpret observations of distant planetary systems. Astronomers have already discovered thousands of exoplanets. Some orbit stars remarkably similar to the Sun. Others circle stars entirely unlike anything in our own neighborhood. Many appear to reside within regions where liquid water could exist. Yet habitability depends upon much more than distance from a star. A planet may orbit within the so-called habitable zone while still enduring relentless cosmic radiation if its star provides only a weak protective stellar wind. Another world might receive stronger shielding despite orbiting a more active star. The interaction between stars and interstellar space becomes one more ingredient in the long and complex story of planetary evolution. The Interstellar probe helps illuminate that ingredient. Its measurements may ultimately improve models used not only to understand our own solar system, but to estimate the long-term environments surrounding distant worlds. The mission therefore reaches unexpectedly into one of humanity's oldest questions. How common might life be? No instrument aboard the spacecraft will detect alien civilizations. That is not its purpose. Its contribution is quieter. It improves our understanding of the conditions under which life might survive across billions of years. Sometimes progress in science comes not through dramatic discoveries, but through reducing uncertainty. Another implication reaches even farther into the future. Humanity occasionally speaks of traveling to another star. The idea has inspired generations of scientists, engineers, and writers. Yet between dreaming of such a journey and accomplishing it lies an enormous gap. Before crossing interstellar space with people, we must first understand it. How dense is the interstellar medium? How dangerous are high-energy particles? How frequently do dust grains strike a fast-moving spacecraft? How stable are magnetic conditions over immense distances? These questions are not abstract. They become engineering requirements for any civilization that seriously contemplates journeys beyond the solar system. The Interstellar probe serves as a pathfinder, not because it travels to another star, because it explores the road that every future interstellar mission must eventually follow. In this sense, its greatest legacy may belong not to astronomy alone. It may belong to exploration itself. History repeatedly demonstrates that pioneering expeditions often appear modest compared with what follows. The first ocean crossings eventually enabled global navigation. The earliest balloons prepared the way for powered flight. The first satellites transformed communications, navigation, and climate science. Voyager itself was once regarded primarily as a mission to Jupiter and Saturn. Today it has become humanity's first ambassador to interstellar space. The Interstellar probe may experience a similar transformation. Future generations may remember it not merely for its measurements, but because it established humanity's permanent scientific presence beyond the heliosphere. That possibility encourages an unusual kind of optimism. Unlike many scientific projects, the mission asks us to think beyond immediate achievement. It reminds us that civilization advances through continuity. One generation asks questions. The next refines them. Another finally answers them. Knowledge grows not through isolated moments of brilliance, but through long chains of curiosity extending across centuries. The Interstellar probe occupies one link within that chain. Its success would not mark the end of exploration. It would simply extend humanity's reach a little farther into the galaxy. And perhaps that is the most remarkable implication of all. The spacecraft may eventually travel 1,000 astronomical units from the Sun. Yet even at that extraordinary distance, it will still remain unimaginably close to home. The nearest star lies more than 40,000 astronomical units away. Interstellar space itself is not the destination. It is only the first step into a universe whose true scale continues to humble every attempt to comprehend it. Seen from that perspective, Voyager's successor is not really teaching us how to leave the solar system. It is teaching us how extraordinarily large the journey beyond it will always remain. If the Interstellar probe succeeds, it will spend much of its existence travelling through a region that no human-built spacecraft has ever explored with modern scientific instruments. Its transmitters will continue sending quiet streams of data toward Earth. Its detectors will sample magnetic fields that have drifted between the stars for millions of years. Its computers will carry out commands uploaded by engineers who in many cases had not yet begun their careers when the spacecraft first left Earth. There is something unusual about a mission like this. Most technology becomes obsolete long before it reaches old age. A mobile phone is replaced after only a few years. Even powerful computers are overtaken by faster machines within a decade. The Interstellar probe is designed according to a completely different philosophy. Its purpose is not to remain modern. Its purpose is to remain alive. Longevity becomes the defining technology. That requirement changes almost every engineering decision. Every electronic component must continue functioning after decades of exposure to radiation. Every moving mechanism must survive years without maintenance. Every scientific instrument must remain calibrated despite temperatures, vibrations, and gradual aging. Unlike equipment inside a laboratory, there will be no technician waiting to replace a failed circuit. Whatever leaves Earth must endure largely on its own. This extraordinary durability raises an interesting possibility. The spacecraft may become something more than a scientific mission. It may become humanity's longest continuously operating machine. Voyager has already demonstrated that such longevity is possible. Launched in 1977, both spacecraft continued operating for nearly half a century, gradually shutting down instruments one by one as their radioisotope power systems slowly produced less electricity each year. The Interstellar probe hopes to build upon that remarkable legacy. Future radioisotope generators are expected to operate more efficiently than those available during the Voyager era. Advances in power management electronics and autonomous software should allow every watt of electricity to accomplish more science than would have been possible 50 years earlier. This improvement is subtle but significant. Deep space exploration is often limited not by distance but by energy. Far from the sun, sunlight becomes too weak for practical solar panels. Every observation, every communication, and every onboard calculation depends upon the finite electrical power carried by the spacecraft. Managing that power becomes a continuous balancing act. Should the spacecraft transmit more data, or preserve energy for future decades? Should one instrument remain active continuously, or alternate observations with others? These decisions evolve throughout the mission. Exploration becomes an exercise in careful stewardship. There is another challenge that quietly grows as the spacecraft travels farther away. Communication. Radio signals move at the speed of light, the fastest speed nature allows, yet even light requires time. A message reaching the moon arrives in little more than 1 second. Signals travelling to Mars require several minutes. At the distance of the outer planets, communication delays extend into hours. Hundreds of astronomical units from Earth conversations become impossible. Mission control no longer speaks with the spacecraft. Instead, it exchanges carefully planned messages separated by vast intervals of silence. Commands leave Earth today. The spacecraft receives them tomorrow. Its response begins travelling home. Scientists wait again. Patience becomes woven into the rhythm of discovery. This gradual slowing of communication produces another remarkable consequence. The spacecraft must increasingly think for itself, not in the sense often imagined in science fiction. It will not make independent scientific decisions or develop its own objectives. Rather, it must autonomously recognize unexpected situations, maintain stable orientation, protect itself from hazards, and continue operating without immediate human guidance. Autonomy becomes less a convenience than a necessity. As humanity pushes farther into the galaxy, intelligent spacecraft become essential partners. Future missions may extend this trend even further. Researchers already investigate navigation systems capable of using pulsars as natural galactic beacons, allowing spacecraft to determine their positions independently of Earth. Others explore artificial intelligence designed to optimize scientific observations while coping with unforeseen circumstances. These developments remain grounded in engineering rather than fantasy. Each addresses the same practical reality: distance eventually forces independence. The farther explorers travel, the more responsibility they must carry with them. Looking still farther ahead, some scientists wonder whether missions like the Interstellar probe represent the earliest chapters of an entirely new era. Not interstellar travel itself. Interstellar preparation. Every great expansion in human history began with reconnaissance. Explorers mapped coastlines before settlers crossed oceans. Surveyors charted mountain passes before roads appeared. Astronomers measured planetary orbits long before spacecraft visited them. The Interstellar probe performs a similar role for the galaxy. It does not carry people. It does not seek another star. Instead, it studies the environment through which all future interstellar missions must eventually pass. In doing so, it quietly lowers the uncertainty facing generations that follow. That may prove to be its greatest contribution. Not a spectacular photograph, not a dramatic landing, but a steadily improving understanding of the space that lies between the stars. Centuries from now, if humanity ever develops spacecraft capable of reaching neighbouring stellar systems within practical timescales, historians may look back upon missions like Voyager and the Interstellar probe as the moment when interstellar exploration truly began. Not because they travelled the farthest, but because they transformed the unknown into something measurable. For now, however, such futures remain possibilities rather than predictions. The nearest stars are still astonishingly distant. No existing propulsion technology can carry people there within a human lifetime. That reality keeps our expectations firmly grounded. Exploration proceeds one careful step at a time. Yet each step changes what the next generation believes is possible. And when viewed across decades rather than years, the distance between impossible and inevitable sometimes becomes surprisingly small. The story therefore returns almost quietly to the same question with which it began. If humanity truly stands at the threshold of a new era of deep space exploration, how should we understand the legacy of the aging Voyagers that first carried us to the edge of the known solar system? At the beginning of this journey, we considered an idea that feels almost instinctive. If Voyager 1 and Voyager 2 were humanity's first great interstellar explorers, then surely their successor would simply be another spacecraft with a larger antenna, faster computers and more capable instruments. A better Voyager. After travelling through the remarkable science behind the Interstellar probe, it becomes clear that this assumption was never quite correct. The true successor to Voyager is not defined by improved technology alone. It is defined by a completely different understanding of what exploration itself has become. When Voyager launched in 1977, its greatest uncertainty lay ahead. No spacecraft had ever flown past Jupiter with such sophisticated instruments. No one knew that Io would erupt with towering volcanoes. No one expected Europa's fractured ice to hint at a hidden ocean. No one had ever seen Neptune's storms from nearby, or discovered the astonishing complexity of Saturn's rings. Every encounter carried the possibility of surprise. Yet, throughout those remarkable planetary discoveries, the solar system itself remained the destination. Everything beyond was largely unknown. Interstellar space was almost an afterthought. Today, that relationship has quietly reversed. The planets are no longer the final objective. They have become stepping stones. The real destination lies beyond the last major orbit, beyond the Kuiper belt, beyond the heliosphere, within the thin and almost invisible environment where our solar system slowly exchanges matter and energy with the rest of the Milky Way. That change reflects more than scientific progress. It reflects maturity. Early explorers naturally begin by examining their immediate surroundings. Only later do they begin asking how those surroundings fit into something much larger. Human civilization has followed this pattern repeatedly. Ancient sailors first mapped nearby coastlines. Eventually they crossed oceans. Astronomers first measured the motions of the planets. Eventually they recognized that the sun itself circles the center of the galaxy. Now, after centuries of looking outward through telescopes and decades of sending robotic explorers across the solar system, humanity is preparing to examine the boundary separating our stellar neighborhood from the wider galaxy. Not because we've exhausted questions closer to home, far from it. Mars continues to surprise us. The icy moons of Jupiter and Saturn almost certainly contain discoveries yet to be made. The atmosphere of Venus remains deeply mysterious. The giant planets themselves still challenge atmospheric physics. Exploration is not moving outward because nearby questions have disappeared. It is moving outward because curiosity expands. Every answer naturally enlarges the landscape of the unknown. This may be the deepest lesson carried by the Voyager missions. Their greatest achievement was never simply reaching interstellar space. It was changing the scale of humanity's questions. Before Voyager, the outer solar system marked the edge of practical exploration. After Voyager, it became the beginning of a much larger conversation. The Interstellar probe inherits that conversation. Its proposed journey toward 1,000 astronomical units is impressive not merely because of the distance involved, but because of what that distance represents. Perspective. From Earth, our solar system feels immense. Neptune alone orbits nearly 30 times farther from the Sun than Earth does. The Kuiper Belt stretches still farther into darkness. Voyager spent decades crossing those immense distances. Yet even after all that travel, our spacecraft have scarcely begun to leave the Sun's immediate neighbourhood. The galaxy is unimaginably larger. Our solar system occupies only one tiny pocket within one spiral arm of the Milky Way. The Milky Way itself contains hundreds of billions of stars. Beyond it lie hundreds of billions of other galaxies. The farther we explore, the more modest our achievements appear. Curiously, this realization does not diminish the importance of exploration. It strengthens it. Knowing how vast the universe truly is makes every successful mission feel even more meaningful. Each spacecraft becomes evidence that intelligence arising on one small planet can gradually extend its awareness into regions that evolution never prepared it to experience directly. The Interstellar probe embodies this quiet expansion of awareness. It will never carry astronauts. It will never plant flags. It will never return to Earth. Instead, it performs something perhaps even more remarkable. It patiently gathers knowledge from a place where no human senses can ever naturally exist. Its instruments become extensions of our own perception. Its measurements become our experience. Its discoveries become part of humanity's understanding of reality. This is exploration in its purest form. Not conquest, not ownership, understanding. Perhaps that is why the mission inspires such quiet fascination among scientists. Its goals are almost entirely intellectual. There are no valuable minerals waiting in interstellar space. No colonies to establish. No immediate economic reward. Only questions. Questions about magnetic fields. Questions about cosmic radiation. Questions about the shape of the heliosphere. Questions about the environment connecting one star to another. These questions may appear abstract. History suggests otherwise. Again and again, knowledge pursued purely for curiosity has eventually transformed civilization in ways nobody anticipated. Electricity, quantum mechanics, radio astronomy, general relativity, each began as an attempt to understand nature. Only later did society discover the practical consequences. The Interstellar probe continues this tradition. Its greatest contribution may not be the one we currently expect. Some future discovery impossible to predict today may ultimately become its defining legacy. That uncertainty is not a weakness. It is one of the reasons exploration remains worthwhile. As the aging Voyagers continue their slow, outward drift, gradually shutting down one instrument after another, as their power supplies diminish, they remind us of something profoundly human. Every generation inherits unfinished journeys. Some are completed, others simply pass forward. Voyager carried humanity to the threshold of interstellar space. Its successor now prepares to take the next careful step. And beyond that step, countless others still remain waiting patiently in the darkness. When the Voyager spacecraft left Earth in 1977, their mission planners knew something that is easy to forget today. The spacecraft were never expected to become legends. They were built to answer specific scientific questions. What did Jupiter really look like up close? How were Saturn's rings organised? What secrets waited around Uranus and Neptune? Like every scientific mission before them, they were designed with finite objectives, finite budgets, and finite lifetimes. No one expected them to become humanity's oldest explorers. No one expected them to remain operational for nearly half a century. And certainly no one expected that decades later they would inspire an entirely new generation of missions aimed not merely at the planets, but at the space between the stars. Perhaps that is one of the quiet lessons hidden inside the Voyager story. The greatest journeys rarely end where they were intended to. They change because the travelers themselves change. Humanity in 1977 looked at the outer planets and saw distant destinations. Humanity today looks beyond the heliosphere and sees an entirely new frontier. The solar system has not grown larger. Our perspective has. That change in perspective may be the most important discovery of all. For centuries, the night sky appeared as an unreachable ceiling above our world. Then telescopes transformed it into a landscape. Spacecraft transformed it into a place that could be visited. Now missions like the Interstellar probe are transforming it once again. The galaxy is gradually becoming an environment that can be explored directly rather than merely observed from afar. It is a subtle transition. No. Yet history suggests that such transitions often reshape civilization in ways impossible to foresee. The first sailors who crossed unfamiliar oceans could not predict global navigation. The first balloon flights did not anticipate modern aviation. The earliest radio experiments did not foresee worldwide communication. Exploration often reveals possibilities long before society understands their significance. The same may prove true for interstellar science. The Interstellar probe is unlikely to answer every question surrounding the heliosphere. It will almost certainly discover unexpected phenomena that no mission planner has anticipated. Some of today's leading theories may be confirmed. Others may require revision. Entirely new questions will emerge, replacing those we consider important today. That has always been the rhythm of science. Knowledge does not eliminate mystery. It refines it. Each generation inherits a clearer understanding of reality, while simultaneously discovering how much more remains unknown. This is especially true in astronomy. Every improvement in our instruments has expanded the universe faster than it has reduced our ignorance. The first telescopes revealed countless stars invisible to the naked eye. Modern observatories revealed billions of galaxies. The James Webb Space Telescope continues to uncover structures that challenge our understanding of the early universe. Likewise, the first spacecraft revealed planets. The next generation revealed planetary systems. The generation after that may reveal the true character of interstellar space itself. There is something deeply comforting about this pattern. It reminds us that mystery is not a failure of science. Mystery is the reason science continues. If every question were already answered, curiosity would have nowhere to go. Instead, every answer quietly opens another door. The Interstellar probe represents one such doorway. Beyond it lie questions about stellar winds surrounding other suns, questions about the evolution of planetary systems, questions about the environments through which future interstellar spacecraft may someday travel, and perhaps many centuries from now, questions we cannot yet even imagine asking. Meanwhile, the original Voyagers continue their own silent journey. Their power slowly declines as radioactive fuel naturally decays. One instrument after another has already been turned off to preserve the remaining scientific capability for as long as possible. Eventually, even those final instruments will fall silent. Their transmitters will no longer send faint radio signals back across billions of kilometers. Mission controllers will wait for messages that never arrive. The conversations that began in 1977 will come to an end. Yet silence does not mean failure. Long after their electronics cease operating, both spacecraft will continue orbiting the center of the Milky Way alongside the Sun itself. For millions of years, they will quietly drift through interstellar space. The golden records attached to their sides will remain carrying the sounds of Earth's oceans, its music, its languages, and its hopes, into a future so distant that human history becomes almost impossible to measure against it. Whether another civilization ever discovers them is unknown. Most likely they never will. That possibility was never the true purpose. The golden record is always as much a message to ourselves as to anyone else. It reminds us that exploration is ultimately an expression of optimism. It is the belief that understanding the universe is worthwhile even when the answers arrive slowly. It is the belief that knowledge should be shared across generations. It is the belief that some journeys deserve to begin even when the people who start them know they may never witness their conclusion. The Interstellar probe carries that same spirit forward. It is not simply another spacecraft. It is a promise made by one generation to the next. A promise that curiosity will continue, that the boundary surrounding our solar system is not the end of our story, only the end of its first chapter. Perhaps that is why the idea of Voyager's successor feels so compelling. Not because it may travel 6 times faster, not because it may reach 1,000 astronomical units, not because it may reveal the true shape of the heliosphere. Those are extraordinary achievements, but they are not the deepest reason. The deeper reason is that every civilization eventually decides what lies beyond the horizon is worth knowing. Half a century ago, Voyager carried that decision to the edge of the solar system. In the decades ahead, the Interstellar probe may carry it beyond. And even then, when that spacecraft has travelled farther than any machine before it, when it looks back toward the sun as nothing more than another bright star among countless others, one quiet question will still remain. If this is only the beginning of humanity's journey between the stars, where will curiosity ask us to go next?